Hello, everybody, and welcome to the Latin American webinar on physics. I am Roberto Lineros from UCN in Chile. I'm going to be the host of today's webinar. Today is the webinar 175, and we have a very special guest for this webinar. He is Martin Hirsch, a professor in the Instituto de Física Corpuscular, a joint institute between the Universidad de Valencia and the CSIC in Spain, in Valencia City. And he obtained his PhD from the Universidad Heidelberg in Germany, sorry. And previously, after that, he did some postdocs in Japan in the Tokyo Institute of Technology, in Germany in the Max Planck Institute for Kernphysik in Heidelberg, and also in Spain in the FIC, and in UK in the University of Southampton. So the title of Martin's webinar is Long-Lived Heavy Neutron Leptons and LHC. Martin, welcome to lawphysics, and the audience is for you. The stage
Thank
is
you very much for the nice introduction. Let me share my screen. Can you see my screen, Roberto?
Yes, I can see perfectly.
Yeah, good. So let's start. Well, thank you very much for the invitation to present this work here in this online seminar. So I would like to talk about long-lived heavy neutron leptons at the LHC. And this is the outline of the talk as I prepared it. So the introduction is mostly about what are long-lived particles and why are we really interested in them now. And then I would like to talk about what I call minimal heavy neutron leptons and LHC. And then we will come to some more specialized subject, which is the effective field theory with right-handed neutrinos. Okay, so let's start. Introduction. First of all, what are long-lived particles really? When I say long-lived particles, I mean particles which travel a finite measurable distance before they decay. Right? So in this plot here, we see a lot of standard model particles, and the plot goes, x-axis is the mass, and the other axis is c tau, which we call the decay length. And of course, there are particles here like the electron, which we think is absolutely stable. So it will travel infinite distance. Whereas the proton, if baryon number is violated, it might decay, but we have only lower limits on the half-life. So again, this is just a lower limit on the decay length. But on the other extreme here, the heavy particles like the Higgs boson, the Z boson, or the top quark, they decay really practically directly after production. So the decay lengths are given here something like 10 to the minus 20 meters. So essentially 0. However, there are some particles here in the immediate range where you can see, okay, C tau in meter is order 1. Well, since this is an axis which goes from 10 to 40 to 10 to minus 20, this order 1 means that, well, P mesons at the LHC, for example, they live something like a millimeter. Whereas the muon that has a C tau of something like a few hundred meters seems very close, but actually there's a lot of difference here. But everything in this ballpark I would call long-lived particles. Now, when you think of accelerator experiments, you would usually actually think that new physics should be discovered here. That is, at the largest masses, which we have not yet probed, to switch on an accelerator with more center of mass energy, you would probe higher masses, right? And that is, of course, what the LHC was built for originally, right? We were looking for new physics, and there were many models. There are many models still, like supersymmetry, left-right semiotic models, models with new scalars, or new vector-like fermions, whatever you can think of. They were all supposed to be heavy. And because they are heavy, one would think they would decay promptly. However, this big point of view has changed a little bit in the past few years. Right? And people have started asking the questions, could we have missed something here in this range where the masses are not so large, but particles actually live for a finite time before decaying? When you hear it for the first time, it's may seem a little bit arbitrary, but there are many models, many example models, which actually predict such particles which are not too heavy and with relatively long lifetimes. The two main group of models which can be mentioned here is some models related with dark matter, or some models related with the generation of neutrino mass, like heavy neutral leptons, which is actually the subject of this talk. Right? In these models, there is usually a reason why the particles are long-lived. And I will come and discuss this in the case of heavy neutral leptons in much more detail later during this talk. But before that, let's look at this slide. I've taken this slide from a review on long-lived particle physics at LHC, which I cite here. This plot shows a very schematic view of a typical LHC detector, and we are looking down the beam line. So the central part of the detector here, and then to the outside. The beam goes along this line. Now, this is very schematic, but this is how particle physics detectors are nowadays built. In the inside here, we have some tracking detector, then comes an electromagnetic calorimeter, then comes a hadronic calorimeter, and outside are muon spectrometers. Right? So this was originally built to detect the decay products of any interaction which happens here in the center. But of course, you can also think of a number of signals which you could have if you have something long-lived, which decays then. Right? For example, we could have a heavy charged particle which is nearly stable, and that would just leave tracks in your detector. This is quasi-stable particles. Another is you could have something invisible which decays to leptons. So it travels a little bit and then it decays, and you see just the leptons, and they don't point back to the origin. You can see the same with multi-track vertices, multi-jets, trackless jets, or you can have disappearing tracks, or you can have something which just emits a single photon and nothing. So there are many possibilities here. This paper summarizes many signals and also many models, which actually, for all those signals, there are known models which predict them, of course. But one point which I wanted to make here is that many models actually predict the C tau, which is larger than its typical detector size, right? So typical detector size is of the order of 10 meters or so. So if you have a decay length, which is, say, 100 meters or larger, then most of your invisible particles would just escape your detector and show up at missing momentum, which is not the best signal to actually discover some new physics. So for that reason, in the past few years, actually a lot of new detectors, a number of new detectors have been proposed, most of them in relation with LHC, but also at other places, which look especially for such long-lived particle signals. So this is summarized in this slide. In the center here, we have the Atlas detector where the interactions happen. And then supposedly some neutral particle is produced there, which decays with a long lifetime. And a number of detectors have been proposed. One of the first one to be proposed was Matusla. Here, this little inset, one can see the schematics. So the Atlas detector would be here 100 meters below ground, and up there, a huge decay volume would be constructed with some trackers on the top of the detector to measure the charged particles from the decay of your long-lived particles, which go through these trackers. Right? This is one of them. Then there was this is relatively at 45 angles, so away from the beam line. Another idea was published a little bit later, which is called phaser. The idea of this experiment was actually, if you look at the scattering cross-sections at a hadron collider, you will see that most of the cross-section is actually in the forward direction. So the idea of those people was, let's go and look into directly back to the beam line, and then we have a large enhancement of number of events if we go really to eta infinity. So the people involved in this experiment, they discovered that around 400 meters downstream of the Atlas detector, there is a little surface tunnel which was empty. So it's not very big, but you could build a small experiment and set it into this tunnel and try to find long-lived particles. This experiment is actually a prototype of this experiment is actually running already. And the experiment actually has two sub-experiments. One is phasor nu that measures neutrino interactions, and the other is phasor for search of long-lived particles. And the phasor nu actually has seen neutrinos produced in Atlas. And they have already made some publications about this, which I found very interesting. Another proposal was Codex B that was meant to be in the hall, or will be constructed in the hall where LHCP is. And there are many others, which I have no time to discuss all of them, right? Some of them were meant to be at the LHC, like Alex or Facet, and June ND. That is, the June experiment has a neutrino beam from the Fermilab, and the near detector can also be used for long-lived particle searches and so on. One experiment which I want to mention, however, is the ship experiment. That is also at CERN, but it's not in the LHC. It actually uses the SPS, which is the proton driver, which is the input for the LHC ring. The protons from that pre-accelerator could be used to make a beam dam experiment where you then search for under you make a beam dam experiment, you make a shield to stop all the charged particles, and then you make a decay volume after the beam dump and search for decays of something in your decay volume here. I wanted to mention this because this ship, after many years, finally last year got a go-ahead of CERN. So this experiment is approved and will, if nothing strange happens, it will be built. Whereas if you look at all the other proposals, it's not clear how many of those proposals will actually be built. Right? Some of them are in better shapes than others. Phasor, as I said, the prototype is already running. Other experiments like Anubis and Methuselah, they are still in design phase. So Methuselah originally was proposed to work above Atlas. Then the Methuselah people discovered that there is a plot of land above CMS, which is actually property of CERN. So they thought, okay, if we go to CMS and the land is ours, then we can dig there a little hole, which makes the detector coming closer to the interaction point. So Methuselah could be constructed with a similar sensitivity and a smaller detector. Right? Similar thing for Anubis. Anubis was originally planned to be in the shaft, in the access shaft above Atlas, and now the Anubis people are discussing to actually instrument the top of the hole above Atlas. Whether these experiments will be built this way is still under discussion, but I think in the next few years we will get an answer which of those experiments will actually be built and which one not. Okay. So this was kind of the introduction, a little bit about the long-lived particle program, which exists right now. And I would like to go my favorite subject in the long-lived particle, and that is heavy neutral leptons. Okay. Why am I interested in heavy neutral leptons? Well, the motivation very clearly is the neutrino mass. Right? More than 25 years ago, Super Kamiokande discovered atmospheric neutrino oscillations. Since then, measurements of neutrino oscillation parameters have improved drastically. We know now most of the parameters in neutrino oscillations with quite good precision. The delta m squared. There are two mass squared splittings. One is the solar mass squared splitting, the other is the atmospheric, and I think it's the solar which is best known with an accuracy of something like 1% or slightly better. Also, in neutrino oscillations, we have 3 mixing angles. 2 of those mixing angles are also measured quite precisely right now. So we are very sure neutrinos have non-zero masses, but there are also some open questions, as you might know. One of the open questions is the absolute mass scale, for which we still have only upper limits. There are essentially 3 types of experiments trying to find this absolute mass scale. One is beta decay endpoint searches like Katrin. The other is neutrino double beta decay. And the third one is to search for effect of neutrino masses in cosmology. These numbers here are rough estimates of what is the current situation. then you have, most of you will probably have seen these kind of plots where the mass splittings and the flavor content of the mass eigenstates are shown in this way with a color code. And we call this side the normal ordering or normal hierarchy when the larger of the mass splitting is on top. And we call this side the inverted ordering if the smaller mass splitting is on top. Which hierarchy is the correct one, we still don't know, although there's a slight preference for the normal ordering nowadays. We also don't know whether there is a CP phase in the neutrino sector. There are some indications for non-zero CP phase, but the reference is really very, very low. And one thing which is especially close to my heart is we don't know whether neutrinos are Majorana or Dirac particles. That is, we don't know whether neutrinos are their own antiparticles or not. And the biggest question of all is not even written on that slide is, of course, what is the origin of the neutrino mass? Well, we don't know the origin of the neutrino mass, but if neutrinos are Majorana particles, then we know that within the simplest extensions of the standard models, all neutrino mass models would lead for Majorana neutrinos to this so-called Weinberg operator, which contains 2 lepton doublets and 2 Higgs doublets. Now, after electroweak symmetry breaking, you replace the Higgs by its vacuum expectation value, and then what you get here is actually a neutrino mass from this operator. So this will be something like V squared divided by lambda will be the neutrino mass times this coefficient. Now, we know that neutrino masses are small. They're sub-electron volt. And this kind of mechanism, which we call the Caesar mechanism, has actually an explanation for that, right? One explanation is, of course, the scale lambda is very high. So if you have a scale lambda, which is of the order of 10 to 14 GeV, then the C can be 1, and neutrino masses are still much below an electron volt. The other possibility is, of course, well, for some reasons, the C alpha beta could be a small number, and then also the neutrino masses are small, and of course, it could be a combination of the above. Classically, when people talked about a seesaw, they always thought of this situation A, that lambda is much larger than the electroweak scale. However, if I just write on this operator, the scale is actually not predicted by anything, so it's a free parameter. So let's look a little bit about neutrino mass models which hide behind this operator. So the simplest thing and the best known is what I call the classical type 1 seesaw. So you open up this operator, and what you put inside is a right-handed neutrino. So if there were no Majorana mass term, then this would be just the Dirac partner of the neutrinos of the standard model, like we see in all the charge fermions. However, being electrically neutral also under SU2, it can have a Majorana mass. And then we can write down a mass matrix which connects these right-handed neutrinos to the neutrinos of the standard model. This famous Caesar matrix, I guess everybody has seen it. And also this little formula here, which expresses now the neutrino mass as the Higgs wave times the Yukawa coupling, that is MD. And we square this and divide by Mn, and this is the neutrino mass. Okay. What we usually don't think so much about is that this also predicts that the mass eigenstates, they are no longer the gauge eigenstates. There's a small rotation between them, or a small mixing angle between what was the doublets. The doublets now get a very small singlet component, and the singlets, they are no longer complete singlets. They get a very small doublet component, and thus a charge current. Okay. Again, Mn here plays the role of lambda in the Weinberg operator. So small neutrino mass by large M. However, you can also see that mixing depends on the same parameter, although in a different combination. So if MD over Mn is a small number, then also the mixing will be a small number. This is important for the phenomenology, of course. But things don't stop here. You can actually find different variants of this type 1 seesaw. Probably the best known after the classical seesaw is this inverse type 1 seesaw, where on top of having a right-handed neutrino, there's an additional singlet fermion. And the right-handed neutrino and this singlet fermion actually are connected by a term MR, a mass term, which conserves lepton number. And the only lepton number breaking term in this model is this little mu. The mass matrix is slightly more big because now we have 3 different kind of states. It looks like this. Now, this is called the inverse seesaw for a very simple reason. If you imagine that this mu parameter here goes to 0, then we have 0 here, 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 here in this mass matrix. And it is relatively easy to convince yourself that if you calculate the determinant of this matrix in this limit mu equal to 0, the determinant is 0. This 0 means that in this limit, light neutrinos would be exactly massless. So this is called the inverse seesaw because the smallness of neutrino masses can now be attributed to the smallness of this parameter, mu. The mixing, however, between the nu and the NR is still given by MD over MR. So if that is small, then this parameter here in front does not have to be as small as in the type 1 seesaw. Similar thing actually happens in this linear seesaw. I think I will skip that in order not to make too many comments on models. Okay, however, I already indicated this, that what is important for us is now, what is actually the decay length of such a right-handed neutrino? So I plotted here the decay length of a right-handed neutrino somewhere between 1 GeV and 1 TeV, so electroweak scale neutrinos. And then, of course, I can fix the neutrino mass to some value. And by the mixing formula, I can calculate what is the decay length of this particle. So this band here from 1 electron volt to 10 to minus 3 electron volts, this is typical decay length which we would expect in a type 1 seesaw if the right-handed neutrino has a mass in this range. So obviously, if you are below 100 GeV, then very quickly these decay lengths are of the order of larger than millimeter to many kilometers, depending on what the mass is and what is the exact light neutrino mass. Okay, that's good. We wanted a long-lived particle. Now we see that smallness of neutrino mass actually guarantee that right-handed neutrinos are long-lived particles. That's good. But we would like to produce these right-handed neutrinos, and that is actually, we do it via discharge current, for example. And then we see that in order to produce the right-handed neutrinos, we get a gauge coupling times this mixing element. Now, this mixing element, again, in the type 1 seesaw, is a small number. That's why these decay lengths are so long. And that means that the production cross-section is suppressed. In fact, the combination of the two actually makes it very hard to really reach the seesaw limit in these long-lived particle searches. However, if I go to the inverse seesaw, what I get is, depending on my choice of the small parameter mu, I get different curves for the decay length. First observation is, if I put the mu of the order of the mass of the right-handed neutrino itself, I reach this gray curve in the background, which is actually this curve here for the type 1 seesaw. So the inverse seesaw contains this seesaw as a limit. However, when the mu becomes smaller, the decay length becomes smaller, which means the mixing is larger. And larger mixing means actually larger cross-section at LHC. So the inverse seesaw is actually, in that sense, a model of neutrino mass which would be easier to observe or exclude in a long-lived particle experiment at the LHC. Good. Now I have always switched between right-handed neutrinos and HNLs, heavy neutral leptons, like one and the other were the same. I would like to specify now one thing, that is, a heavy neutral lepton for me is not a right-handed neutrino. A heavy neutral lepton for me is described by this Lagrangian. This Lagrangian just does what I said previously in terms of a model, but here now model independently. So we have a charged lepton, a heavy neutral lepton, and a W, or a heavy neutral lepton, a neutrino, and a Z boson, and their couplings are the gauge couplings times the mixing matrix element. Now, this Lagrangian plus the mass term for my heavy neutral leptons is what I call minimal HNLs. Why do I want to stress this? Well, this makes no reference to any model. This also gives no explanation of the mass of the N, of course. And it does not even specify whether these heavy neutral leptons are Majorana or Dirac. Right? So if I want to make any contact to neutrino oscillation, I would need to specify where does the mass of this guy come from, and what are actually the relation between the mass of this guy and this coupling here to the W bosons to the observed neutrino masses. However, these minimal HNLs, they are useful because what the experimentalists observe in their searches is this mixing element squared and the mass of this guy. So if the experiments give us a limit on this, then we can translate this into our model parameters. And this translation depends on, of course, what type of seesaw you are looking at, type 1 or inverse seesaw. It makes a different interpretation. But the experimentalists observe this one. Now, okay, what's the status? So I plot here mixing squared versus HNL mass. And these gray areas, these are actually limits from experiments which were done previously in the past. Delphi was one of the LEPT experiments, for example. Right? I've taken these limits from this paper here. But then, of course, the question is, okay, these are the existing limits. What would the long-lived particle searches do for us? So this is a very busy plot now because this one contains expectations of curves for a number of different experiments, all of which do not exist at this moment, but some of which will for sure go ahead. Others may go ahead, right? So we see here at the lowest mass is this dotted line. This is called LBNE. This is the same what I mentioned previously as dune near detector. And then this green line here is the ship experiment, which I also mentioned in the introduction. The red line here is Methuselah, and then there are many others. Okay, here are the references for the proposals, and the figure is actually taken from this paper here. Okay, good. These are here now, if you look at it, you see that these are all far detectors, these proposed detectors. How about the main detector? Well, also for this, there exist papers which make estimates. And here we can see this is now displaced LHC vertex search at the LHC. What it could do with, I think, 3 inverse autobahn. So at the end of the lifetime of the LHC, we would cover this region in parameter space. The comment I wanted to make here is that, okay, this mass range is actually complementary to the far detector. So they are not really competing against each other, they are complementing each other. And the next comment is, yep, there is already a CMS search based on, not on 3 autobahn, of course, but much less. And they currently exclude this part of the parameter space. So clearly, even after this search, there are still more than 2 orders of magnitude to go here in this V-squared space. And also the other experiments here can improve the limits between 2 and 3 orders of magnitude. So there's lots of space for discovery for this kind of particles in the near future. So, yep, good. Now I would like to switch gears a little bit and go to something a little bit more involved. And that is standard model effective field theory augmented by right-handed neutrinos. So I guess everybody knows what effective field theories are in principle, right? The idea is very simple. There is some ultraviolet, some theory in the ultraviolet. The particles there are heavy, which means that at the scale of the mass of these particles, we have to integrate out the new physics. Then we generate a set of operators. These operators we would have to run down to a lower scale, like, for example, the electroweak scale. At the electroweak scale, we would then integrate out the gauge bosons, the Higgs in the top, to come to what is called low energy effective field theory. So your single beta decay experiments are done down here, and you can connect through this way to the new physics via these operators, right? SMAFT has gained a lot of attention recently at the LHC for the simple reason that we have not seen direct signals of new physics. So the question is, can we at least indirectly constrain new physics by giving limits on all these SMAFT operators? Well, people said LHC, they started mostly SMAFT. I'm more interested in a variant, which is the standard model effective field theory, but with new light degrees of freedoms, which are the right-hand neutrinos. This slide shows what I just said in a little bit more formally. So in the standard model effective field theory, we have the original renormalizable Lagrangian of the standard model, to which we add a tower of operators, which take this schematic form. The CK here are usually called the Wilson coefficients. They are free parameters. They're not fixed by anything. The operators, they are constructed out of the standard model fields, of course. And then there comes this lambda to the power of d-4, where lambda is the energy of the new physics. Now, a good thing about this kind of thinking is, of course, since if I increase the dimension of the operator, the dimension of lambda increases, and lambda is supposed to be large, then for larger powers of lambdas, these operators very quickly become irrelevant, and I can stop the series at some fixed dimension. At the LHC, one usually stops at dimension 6, with a few exceptions where one needs dimension 8, but nothing higher than dimension 8 will ever be relevant for LHC physics. Okay, that's a good part. Okay, also at dimension 5, the operator, I want to mention that the dimension 5 is only one operator, which is the famous Weinberg operator, which gives us the neutrino mass. However, at dimension 6, there are already something like order 50 operator structures with 2,500 independent parameters. And that is, of course, the disadvantage of this kind of effective field theory thinking. If you want to be very general, that's what this SMAFT is, and you want to be as model independent as you can be, that's what this SMAFT is, then you pay a price for that. And that price is proliferation of parameters. Now, comment on NSMAFT, right? There's a huge progress has been done in the past 2 years on constructing also the NSMAFT operators. This little table gives the dimension of the operator and the number of free parameters if you add one right-hand neutrino, or like in the standard model, 3 generations of leptons, also 3 generations of right-hand neutrinos. And of course, the number of parameters calculated here are only for the new operators relative to this SMAFT, which contain at least one right-hand neutrino. And again, you can see that these numbers grow exponentially when the number of dimension grows. By the way, you want to check that? You can check this yourself. My friend Renato Fonseca wrote a little computer code in Mathematica, which is called sim2int, which allows you to calculate these numbers automatically in the code. Second comment, which I wanted to make here is, of course, the lowest dimension are the ones which are most relevant for the LHC. And here in particular, at dimension 6, the 4 Fermat operators will be the most relevant for us in the rest of this talk. So these d=6 operators, for Fermat operators, I give them here in form of a table. And the upper half of the table gives operators with at least 2 right-hand neutrinos in the operator. The lower half of the table gives operators where there is only 1 right-hand neutrino in the operator. Okay, I will say more about this, but let me first make one thing, and that is, okay, these operators, they seem to be a little bit arbitrary, they fall from the sky. How could they be? So I wanted to give at least one example model, a very simple example, how such operators actually appear, right? I write here again the Lagrangian of the minimal seesaw models. This is a kind of type 1 seesaw. We have a Yukawa coupling between the leptons and the right-hand neutrinos, and a Majorana mass for the right-hand neutrinos. So that would be the minimal model. Now imagine many BSM models, or all of BSM models practically contain new particles, right? So that could be anything, C prime or leptoquarks. And so I take here as one particular simple example, I add to this Lagrangian now a leptoquark, an uptype type leptoquark, which couples the right-hand neutrinos and the quarks and has a master. Now from this interaction, if this mass is large relative to this to the energy of our experiment, we will integrate it out. So this operation, this interaction squared will lead to this 4 fermion interaction, and then you take a Firth transformation and bring it to the canonical form, and that is U bar U, N bar N, C over lambda squared, which is the C is the H squared, this Yukawa coupling, and the lambda is the mass of the leptoquark. So this way you can see how a simple extension generates this type of operator, and this is actually OUN, and OUN is one of these pair operators here. So just to provide one example. Why did I divide the tables into these 2 structures, pair and simple operators? The answer is, if you have a pair operator, the lightest high-density neutrino will not decay via the operator. It can still decay via mixing if it has a non-zero mixing. But the operator produces the particle but does not decay it. Whereas in the single N operator, the same operator which produces the particle will also lead to the decay. And that makes a big difference on the sensitivity of the LHC to either type of these operators. Okay, here just some example cross sections which we calculate for one particular operator. Dn, it's written here. Cross sections for other operators of similar order of magnitude. To the left is the cross section calculated as a function of lambda, the scale of lambda, and to the right for fixed lambda for 3 different values of lambda as a function of the right-handed neutrino mass. So at 2 TeV, we get order 100 femtobarn or so of cross section. 100 femtobarn doesn't seem to be a large number, but for new physics, it's a large number. Not for standard model physics, but to new physics, is a sizable number. Okay, here this was for pair operator. Here I show cross section as the function of the right neutrino mass for single NR operators. And okay, the colored lines are the different operators, and this gray line is actually N mixing. This is the cross section which you would expect from the mixing term only if the mixing term is of the order of 10 to minus 5. Of course, the production in the mixing is proportional to this VAN squared. So if V is not 10 to minus 5 but 10 to minus 7, then you have to multiply this down by 2 orders of magnitude, and you are actually below the operators already. This is what I say here. Okay. So what is more important, mixing or operator, depends on the scale of the operator very much, and on the size of the mixing. Good. Yeah, now to some results. First for the double N operators. So again, this is in the plane now mixing squared versus the mass of the right-handed neutrinos. And the different lines are now for the different experiments. Again, a very, very busy plot because all kinds of different experiments are plotted here. What I want to stress, however, is look at this axis. So this previously I was showing from 10 to minus 2 to something like 10 to minus 10. And from sub GeV to something like 100 GeV. So this little upper corner here was what I showed for the minimal HNL case. Now, if you switch on the operators and give it a relatively low scale, you can see that the reach of those experiments extends above GeV. And actually, since these pair operators only produce but do not decay the right-handed neutrinos, you would be able to test very, very small mixing. This is indicated here by this type 1 seesaw target region. So this band here is the typical mixing you would expect for type 1 seesaw for the neutrino mass, somewhere between 0.05 electron volts and 10 to minus 3 electron volts, which is a region covered by oscillation experiments, more or less. Okay. Now, of course, I've chosen here one fixed scale of lambda, and you will ask me, okay, what happens if I choose a different scale? I want to show this in a series of slides. So the top figure here is the same as the figure here. The bottom figure is instead of switching on only one operator, I switched on 3 operators. The shape is very similar, but if you look a bit more closely, you will see that the regions in this bottom plot with more operators, of course, larger than the regions here. But that is not the main point. The main point is now we'll vary lambda. So this lambda 2 TeV, lambda 7 TeV, lambda 13 TeV. Again, 2, 7, 13. So above lambda 13 TeV, no new regions will be probed at the LHC, which means that around 15 TeV or so is the end of the sensitivity to these new operators. If new physics is below, somewhere in this range from 2 to 15, we can learn a lot about highly neutrinos if we ever see them. But if the scale is very high, then we are back to the minimal case. Okay, this is for the pair operator. For the single NR operators, it's different. So here, this is for single NR operators, for electrons and muons separately. This is the scale lambda, and this is the right-hand neutrino mass. And the inside of these curves could be probed by searching for displaced vertices with right-hand neutrinos again. So since the operator not only produces but also decays the particle, these lines stop now at around 50 GeV. Because if the neutrino gets heavier, the decay length actually goes like 1 over mn to the 5th. So I could compensate this by choosing a larger lambda, but if I choose a larger lambda, I suppress the cross section and I lose again. And that's why I can test here up to 20-something TeV in lambda and up to 50 GeV mass, but not more than that. Okay. Actually, Roberto, it's now 45 minutes. I have one more section. Do I have a few more minutes or should I skip this?
Of course, you have more minutes. We want to hear about this part.
Okay,
yeah.
okay.
Continue.
No,
continue.
it will take just a few minutes. So if you are happy, I will go over that. Anna left. So right now I was talking about NSMAF, that is effective theory at larger energy. But if you are at lower energy, you should actually integrate out the W boson, the Higgs, and so on, and you arrive at a different kind of effective field theory. In NLF, we can now look, and there are two different types of operators. There are lepton number conserving operators and lepton number violating operators. They are given here in this table. Again, there are many operators. I can just give as examples the NR pair operators. And why would I be interested in this kind of effective field theory? The answer is, before I come to that, I wanted to make a point that here, lepton number violation is a dimension 6 operator, whereas in SMAFT, actually, lepton number violation comes at opt dimensions, as shown in this little table here, right? So this is 3, 6, 7. Why is it then in left at dimension 6? The answer is, well, you integrate out the X, you replace the X by its WEF. So the NR left operators, they have something like V over lambda times 1 over lambda squared. So the additional dimension is actually hidden in this low energy theory. So NR left will be matched to NR SMAFT, and the dimension 6 operators will scale like 1 over lambda squared, whereas the lepton number violating operators, when you scale them up to the SMAFT, will scale as expected as 1 over lambda cube. Okay. Now, why would I be interested in such a low energy theory? Well, the answer is, look at those numbers. This is the number of mesons I will produce at the LHC for 3 inverse femtobarn of data. So 10 to 15 B mesons, 10 to 16 D mesons, right? So if I now have operators in NR left, I can make mesons decay to 2 right-handed neutrinos, or mesons decay to 2 right-handed neutrinos and another meson. And since I have a huge number of mesons, I will be probably very sensitive to these kind of operators. And that was the motivation. Okay, this plot here shows typical branching ratio as a function of the right-handed neutrino mass for a number of different decay modes, switching on one particular operator, this DN pair operator. It's just one example. Other examples are very similar, right? So this full line is the 2-body decay. The dashed lines are the 3-body decay modes. And for large masses, the 2-body decay dominates. For small masses, the 3-body could be important. But this is true for this example of a lepton number conserving operator. If I choose a different operator here, lepton number violating operator, the two-body decay actually dominates everywhere. But again, for a small 10 to minus 3 inverse v squared, I get branching ratios which are of the order of a few times 10 to minus 5, 10 to minus 4. And I have, what is this, B to D? So B mesons, I have 10 to 15 B mesons. So we made estimates, and this is now plotted in, since I have a three-dimensional parameter space, namely the mixing as a parameter for the decay, the size of the operator for the production, and the mass of the right-hand neutrino. I make two-dimensional projections. This is the projection for a fixed C in the plane V squared versus Mn. More interesting is probably the plane, the size of the operator versus the mass of the right-hand neutrino, because here we can reach, again, the different far detectors are given here, and these are the expected regions which we can probe. And just to say, well, if I reach a C 10 to minus 4 or 10 to minus 5, this corresponds to scales of the order of 100 or 300 TeV, which is a huge sensitivity, of course. This is, again, for an example of a lepton number conserving operator. For lepton number violating operators, the limits on the C are similar, but since it scales as 1 over lambda cube, now the limits are actually of the order of 10 to 20 GeV. Still a large number. Okay. That brings me to the conclusions. Well, in the experimental community at LHC, there has been a growing interest in these long-lived particles in the last 5, 6, 7 years. Many of these people who study these long-lived particles are more motivated by dark matter than by neutrinos, but I'm a neutrino physicist, so I'm more interested in these HNL aspects of the problem. As I discussed in the introductions, many proposals exist for future far detectors at the LHC. I'm not sure how many of them will be really built, but at least 2 or 3 of them, I hope. Right? Also, I don't know whether the HNL neutrino exists at a detector weak scale, but once we accept that mass is there, then the smallness of neutrino mass actually nearly guarantees that this particle is a long-lived particle. So it's good in this experimental context. So there's large discovery potential of those experiments in the next 10 years or so, 10, 15 years. They could improve limits by 3 orders of magnitude or more, or, of course, discover new physics. And then in the last part of the talk, I talked about these standard model effective field theory operators and showed that there are also great sensitivity and great opportunities there probing these more exotic kind of models. Thank you very much. That's all.
Thank you, Martin, for your webinar, for your talk. It was very, 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 very interesting. I guess most of the people also that are following us in YouTube are gonna ask questions. So for the moment, before going to the question time, no, after the question time, we're going to do that. If there are questions from here for the audience, maybe Joel or Walter has question for Martin. For sure, Joel has a question. I see his face.
Yes. I was wondering. So thank you for the talk. It was very, very nice. It was very clear. Quite impressive results. I was wondering about your projections for the future experiments like Matusla and Phaser and all of this. So what decay channels are you assuming for the signal? I mean, what kind of signal are these experiments looking at, and what are you considering for this?
Okay, that is a nice question, and of course the answer is depends. Depends on 2 things, right? The first thing it depends on is, are you looking at minimal HNLs or are you looking at the HNLs in more complicated theories? Because in the minimal HNL, the K channels are fixed once you fix the mass and the mixing, right? Whereas if you add 10 operators, the final states actually changes. So that's the theory part, right? The experimental part is, well, different experiments, they are actually sensitive to different things. if you go to the central detectors like ATLAS and CMS, right? they have everything. They can measure the charge of the particle in the decay product. They can tell you its mass. They can tell you the energy which is produced, and so on and so on. Lots of information if it happens in the main detector. However, these far detectors, they are very different, right? Methuselah is essentially an empty decay volume which just measures charged particles. There is no magnet, so they don't even know what is the sign of the charge. They will not be able to reconstruct the mass, only roughly give you an idea. So really, it depends where would you make any discovery, and what kind of model you look at. Now, how did we calculate these sensitivity lines? These sensitivity lines were actually calculated differently depending on whether you have a main detector or whether you have the far detectors, right? In the far detectors like Methuselah or Phaser, what we did is we looked at the decay, and then we looked at calculate the probability of an event produced at the interaction point to decay inside the volume of Methuselah or any of the other experiments into a final state which has charged particles. That's all. When we calculate the probability of measuring any of these in ATLAS, the simulation is much more complicated, much more complete, because there we introduce cuts to get rid of backgrounds. We look at the probability of reconstructing this was an electron or it was a muon. We are looking at the efficiency of the detecting this and so on. So again, depends on what experiment you're looking at. Does this answer your question more or less?
Yeah. No, it's super. So in this sense, so imagine that the whatever long-lived particle is out there has a mass around the GeV or so. So it's inaccessible to ATLAS, CMS, and can be measured in these other ones. So how do you think we would be? Do you think we would be able to get any information? Because there might be several observations, right? Do you think we could get any information regarding what kind of model we might have behind, or is it just okay? There is a long-lived particle. We need to do some more detailed experiments to actually deduce what is behind there.
Yeah, I mean, to really reconstruct the model, caution, these far detectors are not good enough. Sure. But some hints you could get, right? Like, for example, let's compare two things. One is an ALP, an axion-like particle, and the other one is an HNL, a right-handy neutrino, right? The right-handy neutrino, being a fermion at such low mass, will decay into meson and a charged lepton. Okay. The ALP will decay into two identical particles, say E plus, E minus. Right? So the ALP, however, decays in E plus, E minus, and nothing else. Whereas the HNL will decay into E plus by minus, but also in neutrino by zero. So if you can distinguish between those modes just by looking that the number of charged particles is different, right? You might have a chance to say, okay, what the long-lived particle looks more like a fermion than a scalar.
Sure.
These kind of things you can do. But to really identify this was an HNL and this is related to neutrino mass, I think in the far detectors it will be next to impossible. It's different in the main detector, of course, but
exactly.
The far detectors are very poor in that sense.
Right. Super. I'll let the others do more questions. Thank you very much.
Okay. I don't know, Walter, do you have a question for Martin? Otherwise, I have one kind of not naive. I mean, it's naive because one of the strong points of the effective field theories are in the sense that you can map any combination of parameters that usually the UV completed theory cannot reproduce because they are correlated. I mean, they are making correlation in the parameter space of the effective field theory. So with this analysis, is it possible, or there are some tendency to disregard some of the standard UV completed theory, like extra symmetries, extra leptonic symmetries, or any class of higher symmetry that could be broken because of this kind of analysis? I mean, you have, for instance, in this case, you have 54 parameters. But if you analyze the case that it will be completed, for sure, this 54 maybe reduces to 5 or 3 parameters. And then you get all the family of 54 at the low level. But is it possible to try to construct it from the bottom to up in terms of this effective field theory to map which symmetries would be allowed and which symmetries cannot without going from top to bottom in the theory?
I mean, this when the LHC still was not switched on and everybody was doing supersymmetry, this was called the LHC inverse problem, right? You have some observation, now you would like to reconstruct the soft SUSY breaking Lagrangian, right? So the answer to this, also for the EFTs, the answer of this to this is, in principle, yes. In practice, super difficult, right? Because look at this. Let's take just this tune operator as one example, right? So we produce a right-hand neutrino, and you will also see a charged lepton at the origin, correct? Now you can distinguish whether this in the origin was an electron or a muon or a tau. That gives you information on the structure of the parameters here in front, the flavor structure. However, D and U, you could also scatter S and U. That is another combination of parameters. How would you distinguish? It's very hard. And then, even if you could measure all of these 54 and see some of them are 0, some of them are non-zero, would this be enough to reconstruct the UV theory? Probably not. You would probably need to see several operators to get enough constraints to find out what is there that actually generates these operators in the ultraviolet. So the answer is, in principle, yes. But in practice, you need a lot of information before you can really single out models. And if you have for these NR operators only limits, then you cannot learn. You need events.
So in some sense, it cannot help to identify the UV completed theory, but can help to rule out some UV completed theory that cannot reproduce some of the effective parameters if they are measured.
If they are measured, yes, of course. Yeah, if they're measured, yes. I mean, when you see these kind of operators and say you see several of them, then you will quickly get an idea, yeah, what kind of operator you have there. About a flavor structure, that's difficult, that's what I'm saying. But if you find several of these operators, then you get an idea of what is there in the ultraviolet in principle. Yeah.
Yeah, because I was thinking, for instance, another question, in the case of theories with more than one fermion. I mean, I know that this is the idea of your talk was just to have one heavy fermion, but
yeah, these are the parameter numbers for one heavy fermion.
Yeah, exactly.
These are the parameter for 3 heavy fermion.
Two. Yeah, but in the case, for instance, these models of left-right symmetric models, even though they cannot ask you to write doublet, then the fact that to add a fermion that is charged is gonna mess up the analysis, let's say. I mean, could be complemental, but yeah. This is how I think in this kind of popular models that are just extension of the SM.
Yeah. No, but
okay.
Again, the answer is, yeah, we can learn something in principle, yes, but to have the complete information, that will be hard.
No, of course, it's a titanic task to do. So, more questions? Joel has a face of asking. No. Anyway, so from YouTube, we don't have more questions, but also for the sake of the time of the transmission, we are arriving to the hour. So thank you very much, Martin, for your talk. It was very interesting. It's going to be very helpful for future or current PhD students that are working on the field, because they are going to be able to access the video at any time and to consult, and maybe also maybe they want to talk to you at some point to have some details of on the talk. For the people that are following us, just let me tell you that in 2 weeks more, we are going to have our next webinar is going to be Claudio Toni, and he will talk about the atomic anomaly. So for all the people to stay tuned to the next episode of the law physics. And of course, thank you, Martin, again for your talk. It was
Thank you for the
very
invitation.
nice. Okay, so for all the people that are following us, see you in the next Latin American webinar on physics. Bye. Ok, está terminado.